Yeah, 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 yeah. Yeah. 1, 7, 8, 2. Count pairs of nodes. This is a hard problem, don't you know? All right, problem 1782. 1 plus 7 equals 8, minus 2 equals 6, plus 1 equals 7. Notice that crazy cycle? Yeah, me neither. Okay, so let's get right into this problem. Now, if you have any problem recommendations, please leave them in the comments below. Subscribe and like, and I'll go over the problem next because I'm starting to run out of graph problems to do. So I'm thinking about what kind of general category I'm going to approach. I'm thinking we'll go through all the dynamic programming problems on Leetcode. We've kind of already gone through all the graph problems, all the tree problems. So maybe dynamic programming is next or prefix sums. I'm not exactly sure, but all I know is I'm here for a good time, not a long time. Okay, so count pairs of nodes. So you're given an undirected graph defined by an integer n, the number of nodes, and a 2D integer array edges where there's edges I equals uivi, right? So we've seen a lot of problems like this, right? There's n nodes, and then there's edges between nodes, and they're inside of this edges array. Edges between you. You are also given an integer array queries. Let incident AB be defined as the number of edges that are connected to either node A or node B. Okay, so if you have node A and node B, and then there's all these edges coming out of the system, right? Well, in graph theory, right, you have this notion of a degree, right? So the degree of a node is the number of edges that are incident to it. Hence the word, right? Incident, right? So the degree of A would be 1, 2, 3, 4, 5. And the degree of B, I wish I could just stay consistent here, equals, let's just give it 6. 6. All right. Now the incident, then you might say, okay, well, the incident of A and B is just the degree of A plus the degree of B. Now, you may be motivated to consider this as the answer, but I think one thing you should think about is if there's an edge between these two nodes, right? Well, since there's an additional edge on A, well, that would then mean that this isn't 5 anymore, it's now 6. And since there's an additional edge on B, right, that means there is now an additional edge here, and that makes it 7, right? 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6. Okay? But the incident of this is not degree of A, we said is 6, plus degree of B, which is 7, which is 13, right? The incident of this is not 13, it's 12, right? What's the issue? Well, the issue is we're overcounting this node here, right? So since there's this shared edge between these two nodes, we don't want to count it twice, right? Because we counted it once for this A system, and we counted it once for this B system here, right? So what we need to do then is subtract out the shared edges between A and B, right? So the degree of this is still the same, it's still 7, but we want to minus out, right? Let's move this over so it's a little bit cleaner. We want to subtract out this the shared edges between A and B. I'll make that a little bit bigger. So shared edges between A and B, right? So that's really just the number of edges where number of edges AB, right? So what this then does is, well, it says, okay, I'm going to count this once. So it's 6 plus, what's this? 7 minus, well, how many shared edges are there? Well, there's 1 shared edges between these two systems. Minus 1, 6 plus 6 is 12, which is right? Because we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 total edges shared between these two things. So this is the formula generally, right, to get the incident. In summary, right, you add the degree of one node in the incident, right, A, add the degree of the other node in the incident, B, and then subtract out the edges that are shared between them. Because you don't want to count them twice, the shared edges. You only want to count the shared edges once. Okay. Now, so we've covered this. The answer to the jth query is the number of pairs of nodes A, B that satisfy both of the following conditions. A is less than B, and incident of A, B is greater than queries of J. Return an array answer such that the answer length equals queries.length and answers J is the answer of the jth query. Okay, so that's kind of rough. So we have this query value that says like how many incidents are greater than this query value. So let's look at an example here. So we have n equals 4, right? So we'll just draw out the graph. I'm not sure if we'll actually develop the entire graph in the problem, but let's just draw it out for the sake of trying to get a better comprehension of how this is supposed to work. And then you have at nodes 1, 2, 3, and 4. And then you have edges from 1 to 2. You have edges from 2 to 4. You have edges from 1 to 3. 2 to 3, and I'm guessing 2 to 1. Wow, so there could be multiple edges between the same two nodes, right? And that's what we see here. We have one from 1 to 2 and one from 2 to 1. Okay, so this is the graph. So remember, here we have this idea of degree, and we needed the degree to find the incident. So maybe when we do this problem, maybe the first thing we should do is find the degree of each node, right? So we'll just have this degree array. So the degree of 1, right? So we'll have it like this. Yeah, that's fine. So the degree of 1 is what? Well, we have 1 neighbor, 2 neighbors, 3 neighbors. The degree of 2 is 1, 2, 3, 4. The degree of 3 is 1, 2. And the degree of 4 is just 1. Okay. And then what about this idea of shared? Well, the shared is just the number of edges, between, like, we don't need to calculate all possible shared. Like, we don't need to look at the shared between 3 and 4 because there isn't a shared between 3 and 4. So every time we look at an edge, we can just say, okay, there's another shared edge between these two things, right? So the idea is if I look at each edge, so if I have shared down here, let's get this, look at me right. Everything's on the screen. So I've shared down here. Let's call it shared. I don't know why I'm capitalizing everything today. And it'll be actually we'll make it a dictionary. That way we can just add things kind of easily. Right? So if I explore an edge, if I look at an edge, I can be like, okay, well, there's between 1 and 2, there's 1 shared edge. Maybe I look at this edge. Okay, between 1 and 3, there's 1 shared edge. And then I look at the next edge here. Okay. Now we're always going to do the minimum vertice and then the maximum. So I don't put 3, 2. I put 2, 3. And that's going to tie into this idea of A being less than B. But for now, just follow me that when I'm adding edges, I always add the edge in sorted order, like meaning that like 2, even though I like it's 2, 3 is 1. And then maybe we look at this edge. Okay, that means there's a shared edge of 2, 4, which is 1. And then I finally look at this last edge. Okay, 1, 2 is instead of being 1, it's actually 2. Right? So now I have this shared edge idea. So if I wanted to know, okay, what's the incident of 1 and 2? Well, that equals the degree right? I'm just doing the formula we did before, plus the degree of 2 minus shared 1, 2. So I got a little sloppy there at the end. So what's the degree of 1 and the degree of 2? Well, the degree of 1 is 3. The degree of 2 is 4. So that's 3 plus 4. And then the shared between 1 and 2 is 2. So that equals 3 plus 4 minus 2. 7 minus 2 is 5. So is the incident of 1, 2, 5? Incident 1, 2, 5. Right, so calculating the degree, calculating shares, well, we can do that by just looking at each edge. Right, so if we look at each edge, we can add a degree to that edge. Like if we look at this edge here, we can say, okay, that we'll add that information to shared and we'll increase the degree. So let's do that first because this will allow us to find incidents quickly. All right, so we have this shared thing that I said was a dictionary. We'll make it a default dict and we'll set its initial value to 0. And we also have this degree idea, which we'll just say, let's make it a default dict too. I mean, whatever. It's going to have the same runtime, so. All right. And then we'll look at each edge, right, in edges. Well, for each edge, that means there's a connection between two edges. So that means that the degree of each of the vertices on each end of that edge get added 1, right? If I add the edge, if I add the edge 3, 4 to the system, right? That means I'm increasing the degree of 3 by 1 and I'm increasing the degree of 4 by 1. Right, so then the increase of this will become 3 and this will become 2. And that makes sense, right? 1, 2, 3, 1, 2. All right, so that makes sense. So we increase the degree of U by 1. We increase the degree of V by 1. And we increase the fact that there's a shared edge between U and V. So there's a shared edge between U and V, and we add plus equal 1. Now, this is close to being right. I would say the only thing we want to think about here is, remember, in this problem, the original edge was 2, 1 and 1, 2. Right, these are the corresponding edges that created these two links, right? This 1, 2 created this 2, 1 created this. The basic idea is like, what I want to get at is, I don't want this system to think that there's a difference between 2, 1 and 1, 2, right? That's the same edge. So in order to combat that, I'd say the min of U and V is one side of the edge, and the max of U and V is the other side of the edge. And that'll just make sure that it's counting the same edge twice instead of thinking that they're different edges, right? Because it's not a directed graph, it's an undirected graph. So UV and VU are the same edge. So we're just doing this to make sure that the shared array gets populated properly. Okay. And I won't go through why. So then let's print degree and let's print shared to see if it makes sense. Right. So does this match what we have in our system? Yeah, so we had 1, had 3. Right, remember I added an additional edge. It was this one, right? I added this edge. This edge actually isn't in the system. Right? I just added that to prove a point about how edges are added. So the degree of 1 is 3. The degree of 2 is 4. Yep. The degree of 4 is 1. The degree of 3 is 2. 1 and 2, they have shared 2. 1 and 3. 1, 2, 3, and 1. 2, 4, and 1. Okay, so this looks correct, right? This shared idea and this degree idea. Now, to solve this problem, there's a very intuitive, easy solution, which takes, what would be the runtime? It would take n squared time, right? Or n is the number of vertices. Because what you could do is look at the incidence between each vertex, right? You could look at, so we'll do the inefficient solution quickly, right? We'll say res is going to be the solution. And then we'll look at the incident. So we'll define a function. Actually, no. So we'll look at each query in queries. And what we'll do is we'll say, well, we'll look at the incident pairs for each node. So we'll say for u in range 1 to n plus 1. So that'll be each vertex u. And for v in range u plus 1 to n plus 1, right? We don't want to overcount. And in order for the query to be accurate, a has to be less than b. So let's just call these a and b, so it's a little clearer what I'm saying here. U plus 1 of n plus 1. And then we'll say, well, if... Okay, we will make a function, I guess. If the incident of a and b is greater than q, where q is a query, right, we'd say, okay, let's call this answer. Answer equals 0. If that's the case, then answer plus equals 1. And then at the end, after you check everything, you say res append, so the solution append answer. So what this is basically saying is you take a query and then you check every possible incident and see if the query value is greater than it, right? You populate all of these values and see if the query value, and it's not greater than, is less than that value. And if it is, then you know that you have a valid solution. Okay, so that would mean that the runtime of this is then what? Or how would you find the incident? So def incident of AB, we're just going to do the formula, right? We return the degree of A plus the degree of B minus shared of AB. And A is always less than B, so we know that that'll fit in. And then at the end, we just return res. Seven five or 6 5. 3 4 5 1 6 9. Get low, get low. Sorry, give me a second. I'm trying to figure out. It's supposed to work, so. Oh, I call this U. Weird. Forgot to change that. All right. So this will work, right? Because what we do is we just say, well, we're trying to find the number of pairs of nodes that satisfy both of these conditions, right? So we can just look at all pair of nodes and see the incidence for each pair for all pair of nodes, right? Because this will look at all pair of nodes and then see if it satisfies this condition, right? Now I'm gonna submit this, but I'm guessing that this is going to be a time limit issue, right? This is gonna be too slow of a solution, right? So time limit exceeded. Why? Well, first, because there's obviously a more efficient solution, but this takes this operation here, right? We have to look at each pair of vertices, so that takes n squared time. Right, and then here we have to do that for each q vertices, where q is the number of queries. No, not vertices. We have to do q queries, and for each query we have to do O of n squared pairs. So that means the total runtime of this whole thing is O of q n squared. So that's just too slow, right? It's too slow to do all of these operations. So this isn't going to work. So this is the most intuitive way of doing this, right? It's like, okay, if you want to know the incident for each pair of vertices, if it's greater than the query, then I'll just look at each pair of vertices and check if their incident is greater than the query, right? Good. But there's actually a much faster solution. So one thing you can think about when you look at this problem, and we'll look at the one we did again. Maybe we'll go back in time to try to get it to somewhere where before it got all crazy. Okay, that's good enough for me. So we know what incident is, so we can erase this. So I guess what you can do, what you can think about here is, well, what? If we were to look at this system and not consider this shared idea, right? If we wanted to look at the degree of both of these nodes and find out if it's greater than a query, well, one thing you could do is you could look at this and you could sort them based on their degree value, right? So you could say, well, what if we looked at degree sorted, right? And we looked at the actual vertices themselves. Well, the smallest vertice, right, the vertice with the lowest number of edges is 4, right? So that means 4 would be the smallest one. And then we would have, there's 4, so let's just do that. Okay. And then after 4, 3 has 2 edges, right? I'm just counting the number of edges that each of these systems have. And then 1 has 1, 2, 3 edges, and 2 has 4 edges. Oh, I draw this wrong thing here. 1 has 3 edges, 2 has 4 edges, right? So these have value, 4 has value 1, 3 has value 2, 1 has value 3, and 2 has value 4, right? So what that basically means is if I look at this system sorted, I don't actually have to look at each pair of vertices. So this is a little trick, and I forgot what the concept is that's going on here, right? This isn't like a graph. Like this is a graph problem, but this approach to solving it efficiently is not a graph topic, right? It's not like we're going to run DFS or run topological sort or something like that, right? For this problem, although it's a graph, there's a different topic that covers this idea of efficiently solving this problem, right? And I guess the idea is well, if we were looking for something, not with incident, let's say we were looking at total degree, incident 3. We'll just start there. All right, we wanted incident of AB greater than 3. Right, so maybe query value equals 3. And is that one of the... Yeah, so query value equals 3, right? Well, if we were looking at this value and this value, so we had 2 pointers, L and R, right? We had 2 pointers, L and R, and the incident value of this thing, right, is 4 plus 1 is 5. Okay? So the value of the degree of 4 plus the degree of 5, or of 2 equals 5, right? So the degree of the smallest vertice, right, this left one, and the degree of the largest one is 5, which is greater than query. Now, this is the smallest value from the left. So that means that all subsequent values are greater than L, right? Like the values only get bigger as you go to the right. So if the value only gets bigger as you go to the right, if it works for L, it's going to work for everything greater than L up to R, right? No matter what, right? Like if I'm the poorest person, I'm not. Big flex. No, I'm joking. I'm not wealthy. But if I'm the poorest person in the group and the richest person in the group and we're all sorted, right? So I'm at the very left and he's at the very right, right? He's the richest, I'm the poorest. If our money together can afford something, that means that everyone else in between us with the richest person can also afford it, right? Another way of thinking is like if there's a basketball hoop and we can stand on each other's shoulders to reach the basketball hoop. If I'm the shortest person and the tallest person, if the tallest person puts me on their shoulders and we can reach the basketball hoop, that means that everybody else in between me, the shortest person, and the tallest person, if they're matched with the tallest person, can also reach the basketball hoop, right? Because if this person is this size and you had people sorted by size, I'm just going to give this point one more time so it's really clear, right? So we had these 4 people and they're sorted by size, right? And then you had a basketball hoop here of this size. If the shortest person, which is our left, right? Because we have this idea of left and this idea of right. If the shortest person, let's make this basketball hoop a little bit taller. If the shortest person and the tallest person can exceed the height of this basketball hoop, well, then that means that everybody else in between can also, right? Because they're only taller. So I guess that's the idea of this problem to efficiently find pairs, right? So I don't need to look at each pair of persons. I can just sort them in order. And I say, well, you're the shortest person on the left and I'm the tallest person on the right. And you and me together can reach the basketball hoop. So that must mean that everyone in between the shortest person and me, the tallest person, must also reach the basketball hoop. So that's basically the idea here, right? So I don't need to count all pairs of nodes. Since they're sorted, it's an invariant that everybody larger than L can also reach can be larger than the query value, right? So if L and R can reach is greater than the query value, that means everything in between L and R can also reach the query value, right? So that means then if, well, the degree at L plus the degree of R is greater than the query value, then that would mean that the answer is going to have how many solutions? Well, it's going to have R minus L solutions. So I'm going to plus equal R minus L, right? Because R minus L, this is 0, 1, 2, 3, right? Because these are pointers, right? This is index 0, index 1, index 2, index 3. There's 3 solutions here, right? Because R can go with L, that's 1 solution. R can go with 3, that's 2 solutions. R can go with 1, that's 3 solutions, right? So 1 solution, 2 solution, 3 solution. Okay. And if that's the case, right? So in this problem, what are you going to do then? If it's greater than Q, well then you can just decrement R. Right? Because you don't want to increment L because you already know intuitively that it works for L, right? If this is the case where it's greater than, you wouldn't just increase this by 1. Right? Because you already know this solution works. So obviously that's not what you're going to want to do, right? Because you've already accounted for that, right? We know for a fact if the shortest person and the tallest person can reach the hoop, then the second shortest person, right, which is this person, the second shortest person, which is this person, can also reach the hoop. So then maybe what you want to check again is like, okay, maybe the tallest person is extraordinarily tall, which is allowing all these people to reach the hoop, so we should decrement R by 1. Now, if R and L can't reach the hoop together, then you need to increase the height of the people related, right? The 2 people. So you increase height by increasing L. So that's the general idea here. So instead what we'll do is we will quickly sort degree based on the index. So we'll call it degree index. And it'll be sorted range of n from 1 to n plus 1, I guess, because those are the node values. And then the key will be lambda n or u degree, or let's call it a because there's this idea of ab, degree of a. Okay, so now we don't need to look at all n squared edges here. What we do instead is we say, well, there's an L and there's an R pointer. So we start L at the shortest person, right? So we start L at the smallest degree system, which is 0, and then R is n minus 1. And then we're going to say, well, while L is less than R, we'll have it that, what? We'll say if degree of di at L plus degree of di at R, right? I'm trying to get the degree of these things in order. So I'm using this di because it's the sorted range. So it's di is basically this degree sorted thing here, right? Where each vertice is inside of the array. So if the degree I di is greater than LR is greater than Q, well, then it's the system that we had here, right? We established then answer plus equal R minus L, and we want to decrease R. So that's the case. Answer plus equal R minus L, and we want to decrease R minus 1. Otherwise, it's not a solution, so the people aren't tall enough, so we want to increase L by 1. All right, and then we return res. So you might look at this and say, well, okay, it works, but your solution, right, like what we did here doesn't even capture this idea of shared. Okay? So it doesn't even capture this notion that there's this shared array which is going to affect the degrees, right? Because if like you don't want to overcount, right? Because right now our system, if we just consider degrees, just like we covered in the beginning, we're overcounting because there's shared edges between systems. So what we want to do now is say, well, we have a system of incidents, right? We've counted all the incidents, but we haven't considered the fact that there's shared edges. So what we should do now is look at each edge in shared, right? And we'll say, well, if we thought this was a solution, right? So basically what I'm saying now is like we've added in all these things that are potential solutions here into answer. But it's possible that they aren't actual solutions because they have shared values which decrement the actual incident, right? So like we thought they were solutions, so we added them into answer, but they may not actually be solution because they have shared edges, right? For example, in this system, right, if we said incident of AB equals 6. Well, the degree of this is 3, and the degree of this is 4, right? So that's greater than, or let's say the query equals 6. The incident of this and this, if you just count the degrees, is 7, and 7 is greater than 6, right? So we may add that to the answer. But the problem is that this is not a solution because the shared value is 2. So it's going to decrement this thing to 5, right? So if I ran this same code again, and I just created a custom example, it's going to fail, right? So if I go to this test case and I say, well, I want something greater than 6, we're going to get the wrong answer. Oh, query always has to be less than edges. So 0 and 4. Whatever. You see what I'm saying, right? So I flew too close to the sun there. So if the degree of this is greater than Q, so this means that we ended up counting it, and minus shared of UV is less than or equal to Q, right? So this is basically saying if we ended up counting this into answer, right? That's what this means here. But the actual solution is less than or equal to Q, right? The actual instant, which is this formula, is less than Q. That means we've overcounted this one. This actually isn't a solution. We thought it was, but it really isn't. And with that, that is the answer to this problem. So we basically look at everything as just degrees so that we can use this efficient sorting idea. And then we remove the ones where they're not actually incident solutions. And then we get the answer wrong because we're idiots. Okay. Oh, because I left LR in here. So degree of UV. We'll call this AB, actually. Let's just, and it wouldn't be there. It'd just be degree of A and degree of B, because we're talking about just the vertice AB, right? Not the vertice that's in the sorted order at L and R. So degree of A and B minus this A and this B. Okay. All right, cool. There you go. So what's the runtime of this? Well, it's going to be dominated by this system here. We have to look at each edge, right? So if there's we have to look for each query, right? So for each query Q, we have to look at the degree of each node. So there's n nodes. And then we have to look at each edge to remove the things that we overcounted. And there's e edges. So that's big O of Q of n plus c time. And then for space, well, we have to keep the degree of each node. So there's n nodes. And we have to maintain that information. And we also have to maintain information about each edge. So there's e edges, right? So big O of n plus e. That's time space complexity. So that's pretty much it for this video. I'm going to quickly just make this shorter because this can be way shorter. But that's not really important. I'm just doing it because I like to have fun short solutions. Right. Degree of U, degree of V. Shared of this. Everything just gets incremented by 1. Okay, so degree of U. Degree of V plus 1. Plus 1. And then this we didn't end up using anymore. I guess we could have, but whatever. This we've already defined again. This can go on one line. This can also go on one line. This can also go on one line. See how these things can get really short? This can also go on one line. That we're kind of stuck. Let's remove these lines between. Run that again. Okay, cool. All right, everybody. Have a good one. Bye-bye.